the topics for today, and I'm going to go very briefly like what is machine learning. Sorry if it's something that you have heard many times over, but machine learning is a part of artificial intelligence, and artificial intelligence in itself, it's a process where you try to distill knowledge in a way that you try to enable decision making without a human intervention. And there are two ways to do that. The first one, which was at the beginning of the field, was a rule-based way. And what is really happening here is that you discretize the knowledge into a finite set of conditions, and you devise a search operation. But the problem with this is that it's not scalable, and some constraints, some search problems are harder than NP-hard. And to mitigate this challenge, machine learning came along, and instead of handcrafting features or to perform the search operation, machine learning enables you to extract knowledge from the data, and then this knowledge can be accommodated into continuous parameter settings. This way, you can scale the process as you increase the training data, and the inference model the inference can be done in a constant time complexity. But the price you pay for this is that you get an approximation for the optimal solution. But this approximation becomes better as you add more data. But of course, this doesn't come without a price. So there are some certain assumptions that you have to make about the data before you learn from there. And the first assumption, it has a geometric interpretation that is the smooth manifold assumption. And what it means that if you are given a training data, and these training data are a certain dimensionality, and you can think of this training data as points in this high dimensionality space. And the valid data will be sitting on a smooth manifold, and the invalid data, that means the noise, will be sitting outside this smooth manifold, but they both reside in the same space. And the data here are comprised of discriminative features and non-discriminative features. And what do I mean by that is that if you look at these both pictures of Einstein, what enables us as humans to recognize that these two pictures come from the same person are the discriminative features, and everything else it's not. So in a machine learning, you try to devise a method that is not the response it's invariant from the non-discriminative features. And what do I mean by that is that if in case of classifying two types of objects like cats and dogs, the cats will always be projected in the same space, irrespectively of illumination of the cat pictures and so forth. And the same for the dog. And the other assumption is that the data should co-vary with the discriminative features. That means that if eyes or a mouth vary a bit, there will be some variation in the space where the cats are embedded. So this is the geometric assumption that you make about the data in order to learn from the data using a parametric model. Because the free lunch tells us that if you cannot make any assumption about the data, you cannot actually learn anything from them. And to make a decision, you have to carry the data with you always. The other assumption that enables us mostly scalability, apart from learning, is that a statistical one. And this assumption tells us that in order to have a good training set, the data should be statistically independent from one another, but also they should come from the same distribution. And why is it important to have them independent? This is important because you can discretize what is called the risk, the right-hand side of the left-hand side of the equation, because without having them independent, you cannot perform Monte Carlo on the risk to treat the data individually at the test at the training loss. And why we need them identically distributed? This is important because if you train your data on a training set, and then once you move this model into the production, but if the distribution of the test set is not the same, your model will fail doing any decision making. And this is one of the key challenges that we're going to deal during this presentation. And a good side effect of this is that if you increase the number of data to infinite, like the risk becomes 0. And what it means that the model should be 100% correct as you add more data if the data are identity IIDs. And this is an example where AlphaGo was able to outperform humans because he was trained in a much bigger data set than any human was able to do. And they were able to make this data independent from one another using something called experience replay. And when you have a lot of training data, you cannot normally fit them into your memory because there is no RAM that can allocate like a lot of data. That is usually the case when you train big training models. And because data are considered to be IIDs, you use a stochastic gradient descent. And what do we mean by that? That instead of treating the data at once, you can sample from this training data with or without replacement. And then you can perform gradient descent only on this subset of samples that is sampled from the training set. And then you can, if you do that, you're trading time for memory, but you can ensure convergence. I was reading the other day a very nice paper from Bernard Schkolkoff, and he gave an example of why we have to learn only from training data. And he bring an analogy from conservation of energy. That means that what we do in engineering is that we convert energy. And similar thing should happen with your information from the training data. That means that all the information that you have in the big data, you should be able to accommodate it into your deep learning methods. And once you do this, you can go on and performing data-driven decision making. In our presentation, we're going to be focused mostly on classification and clustering, but you could also do segmentation, detection, regression, but that's not the topic of today's presentation. And deep learning was one of them. It's a revolutionary for some reasons. And the first one is because traditionally, like pre-deep learning area, what was happening in machine learning is that if you had a lot of training data, you have to engineer a feature extraction, and then with the features that you extract here, you have to train a classifier. But the problem here that you introduce a lot of bias with this feature extraction, and you are not learning just from the data, but you are having your personal bias into the process, and that was suboptimal. But with the deep learning, you can remove the human from the loop for this task specifically, and you can enable a better learning. And what do I mean by a better learning is that as you add more data, the performance accuracy of the deep learning doesn't saturate as it does with the previous machine learning techniques. And with this, different applications were like a milestone. The first one was Atari game, where everything, the DeepMind was able to introduce a machine learning, deep reinforcement learning approach that learns just from the pixel values to play the Atari game and surpassing humans. And that was the beginning of a series of applications. But applications that impact human are like stemming from, ranging from healthcare, where a professor from Stanford was first to show like in a Nature paper that he can perform skin cancer detector using like an inception net. And people are going to more like even more practical implementations, such as a self-driving car, where semantic segmentation is a very necessary key component. to do like autonomous driving. But Alex Kendall is kind of a pioneer in this field, and he said that when you do deep learning, you don't account so much for uncertainty with traditional models. And in a predictive response that you get from a deep learning, you have two types of uncertainty. That means the data uncertainty and the model uncertainty. And what do I mean by these two is that the data uncertainty, it's something that is intrinsic to the data, and then something that you cannot do much about it other than modeling it. That means other than properly quantifying it. Epistemic, apart from data uncertainty, the model uncertainty is the uncertainty that is a misfit of your assumption about the data that you encode in your model. And that's something that you can reduce. And there are different techniques you can deal with that. But how is uncertainty important in practice? Let's say that we have a classifier, which is something that I worked on one paper. And let's say that you have a very well-trained classifier that can tell apart cats versus dogs. So the method is very good at doing that. But when it comes to having a horse as an input, the method has been trained to tell only whether it's a cat or whether it's a dog, and it's not capable of telling it's neither of them and I don't know. And one might think that okay, but this is a simple example. You just retrain the model with the horses, and you collect a lot of training data on the horses, and you can mitigate this problem. But this is not as simple as that, because the out of distribution data, it's anything but what is in the training set. And that means that it's an open set detection problem. And if you follow that line of thoughts, then you have to introduce infinite amount of classes in a training set. But we follow a different approach to address